Have you ever really stopped to think about what's happening when you flip on a light switch or plug in your phone? It feels like magic, but it's not. It's an invisible force. And today, we're going to break down the incredible principle that literally powers our entire modern world, electromagnetic induction. So, let's start with a question. A huge question that completely obsessed scientists back in the 19th century. They knew for a fact that if you run an electric current, you get a magnetic field. It was like a law of nature. So the big, obvious next question was, can we do it the other way around?
And that one simple question leads us right into our first section, because chasing down the answer to this, well, it would change absolutely everything.
Okay, so you've got to picture the scene. It's the early 1800s, and scientists like Hans Christian Ørsted had already figured out this amazing trick. Run electricity through a wire, and boom, a magnetic field just appears around it. That was the established science. It was a known rule of the universe.
This is where the star of our show, Michael Faraday, comes in. He was totally captivated by this idea. He just thought if electricity can make magnetism, it has to work the other way. There's a symmetry to it, a beautiful elegance. And he became completely obsessed with proving it.
But here's the frustrating part of the story. He tried everything. He'd take a super strong magnet, put it right next to a coil of wire, check his meters, and nothing. Not a flicker. For years, every single experiment was a dead end. The answer to his brilliant question seemed to be a big, fat no. But Faraday was not the kind of guy to just give up. And his persistence led him to a breakthrough. Which brings us to our second section, where he finally finds the secret ingredient to this whole puzzle.
And this was it, the big aha moment. Faraday noticed something really weird. He'd only ever see a tiny little blip of current for a split second when he was first connecting his battery, or, and this is the crucial part, when he was moving the magnet. A magnet just sitting there did zilch, but a magnet in motion, that was everything.
And this was the fundamental insight. This is the whole game, right here. It wasn't the magnet itself that mattered, it was the change. A changing magnetic field is what creates the current. It's a dynamic thing, not a static one. That was the missing piece.
Okay, so there's a technical term for what's changing, and it's called magnetic flux. Just imagine a bunch of invisible lines of force coming out of that magnet. The flux is just how many of those lines are currently passing through your loop of wire. When you move the magnet closer, more lines go through. When you pull it away, fewer lines go through. That change in the number of lines, that's induction.
So Faraday wrote this all down into two super important laws. The first one is simple. If you change the magnetic flux in a coil, you will create a voltage, period. And the second law, it's just as intuitive. The faster you change that flux, by moving the magnet quicker or using a stronger magnet, the more voltage you get. It's that simple. More change means more power.
But wait, there was another mystery. The current didn't just appear out of nowhere, it always flowed in a very specific and honestly a very strange direction. And this leads us to our next big idea, the law of opposition.
So remember how any electric current creates its own magnetic field? Well, the new current that we just induced, it instantly creates a second magnetic field in the coil. So which way does that new field point? The answer points to a deep, fundamental rule of the universe. Nature doesn't like change. It always pushes back against what you're trying to do.
I love this analogy. Think of it like a really contrary relationship. When you try to move the magnet closer, the coil immediately says, whoa, you're too close, and it creates a magnetic pole that pushes you away. It repels you. But the second you start to pull the magnet away, the coil flips and says, wait, don't go, and it creates the opposite pole to try and pull you back in. It always does the opposite of what you're doing.
This whole push and pull thing is known as Lenz's law, and it's basically nature's way of conserving energy. The induced current always flows in a direction that fights the very change that created it. It makes sure you can't get energy for free. You always have to put in work against this magnetic resistance.
So this whole idea of opposition, this resistance to change, it's not just some weird physics quirk. It is the literal foundation of our entire electrical world. So let's see how we actually put it to work.
Okay, this is the basic recipe for pretty much every power plant on Earth. You take a big coil of wire and you put it in a magnetic field. Then you use some other force, like wind or steam or falling water, to physically spin that coil. As it turns, the magnetic flux passing through it is changing constantly. And what did Faraday's law tell us? Constant change creates a constant current.
Seriously, just let that sink in.
Whether it's a huge hydropower dam, a giant wind turbine, or a nuclear power plant, they are all just incredibly complicated machines for doing one simple thing: spinning a wire in a magnetic field. This one little discovery is the engine of our civilization.
All right, before we wrap this up, there's one more wonderfully weird side effect of all this. We have to talk about the strange world of eddy currents.
Okay, check this out. It's a famous experiment. You drop a powerful magnet and it just falls. Duh. But now, take that same magnet and drop it through a thick copper pipe. And remember, copper isn't magnetic. And something totally bizarre happens. The magnet falls in this eerie, silent, slow motion. It looks like it's sinking through invisible molasses. So what on earth is going on?
Well, the answer is something called eddy currents. As that magnet is falling, its moving magnetic field is inducing currents, not in a nice neat wire, but in the solid metal of the pipe itself. And these currents don't flow in a straight line. They swirl around in these little localized whirlpools, like eddies in a river.
And just like Lenz's law predicts, these little swirling eddies of current create their own magnetic fields that oppose the motion that created them. What's the motion? The falling magnet. So these fields push upward, fighting gravity and creating this incredibly powerful magnetic brake. And that leaves us with a really fascinating thought to end on. From the giant generators powering our homes to the silent magnetic brakes in a simple copper tube, our entire electric world is built on this fundamental law of opposition, this tendency for nature to push back against change. It just makes you wonder, what other profound, invisible forces are out there, hiding in plain sight, just waiting for the next person to come along and ask the right question?